You've probably used a dozen of these before you even had your morning coffee. The spring. I mean, it seems so simple, right? Almost forgettable. But what if I told you that hidden inside this tiny, humble coil is a world of science so complex that it pushes the very limits of modern engineering? Let's find out what's really going on inside.
Yep, you guessed it, the spring. From the heavy-duty coils in your car's suspension to the tiny clicker in your pen, they all rely on the precise, predictable power of stored energy. But the real question is, how on earth do engineers make something that can be so wild, so chaotic, so predictable?
Okay, so we're going to move way beyond the slinky you played with as a kid. This is about high-performance engineering, where even a tiny miscalculation can have absolutely massive consequences.
Springs are really the unsung heroes of the mechanical world, you know? They're constantly absorbing shock, storing energy, and applying force. But as our technology gets more and more advanced, the demands we place on these humble components, well, they're pushing engineers to the very edge of what's possible with modern physics and material science.
And that right there brings us to the core problem, what engineers call the non-linear challenge. This is where the simple textbook idea of a spring just completely collides with messy, complicated reality.
So, in school, we all learn about linear springs. It's simple. You push it a little, it pushes back a little. It's a straight line on a graph, totally predictable. But in the real world, high-performance springs are non-linear. Their resistance changes in these complex, almost chaotic ways, depending on the load. And let me tell you, that kind of unpredictability is an engineer's absolute worst nightmare.
And that's the whole ballgame right there. When you're designing a suspension for a race car or a critical part in an airplane, hard to predict is not something you ever want to hear. So how do engineers actually tame this complexity?
Well, they fight complexity with a really powerful three-pronged attack. They combine old-school theory, cutting-edge computer simulation, and rigorous real-world testing. Let's see how these three pieces fit together.
You see, no single method is enough on its own. It's this constant cycle. It starts with the pure math, the analytical models that act as a kind of blueprint. Then they take that blueprint and build a digital twin, using powerful simulations, like the finite element method. This basically breaks the virtual spring down into millions of tiny pieces to predict its behavior. And only after that virtual spring passes the test do they build a real one for physical validation. It's this constant loop: predict, test, and refine, over and over.
And this toolkit is being used right now by researchers all over the world. You've got someone like Svetikanen, who's using pure math to design metastructures. These are materials with properties you just don't find in nature. At the same time, Guo's team is in the lab, physically testing new composite springs, blending materials like carbon fiber and steel. Every researcher is using a different mix of these tools to solve their own unique piece of this giant puzzle.
So now that we have the tools, what are the specific problems they're trying to solve? Well, two of the absolute biggest are vibration and the internal forces of stress and strain.
Okay, so every object, every single system has a natural frequency. Just think of it like pushing a kid on a swing. If you push at just the right rhythm, that's its natural frequency, the swing goes higher and higher with very little effort.
Now that's all fun and games on a playground swing. But in an engine or a bridge, if an external vibration happens to match the system's natural frequency, you get resonance, and that can amplify vibrations until the entire structure literally tears itself apart. This is why getting that frequency calculation right is, quite frankly, a life or death situation.
And what's really fascinating here is just how sensitive that frequency is. Research from engineers like Zhou and Zhuang shows that something as seemingly simple as how the springs are mounted, or even just how many are stacked together, can completely change everything: their vibration, their ability to absorb energy, their entire dynamic response.
So that's all the external behavior, the shaking and moving. But what's happening on the inside? When a spring is compressed or stretched, incredible forces are at play deep within the material itself. This is exactly where those numerical simulations we talked about become so incredibly critical. Using the finite element method, engineers can create a super detailed digital twin of a spring and see precisely where stress is concentrating. They can find the microscopic weak points before they ever have a chance to grow into a catastrophic fracture out in the real world.
And the level of detail they go into here is just mind-boggling. I mean, they're analyzing the precise curve where one coil transitions to its arm, the exact roundness of the final coil, even tiny microscopic stresses left over from the manufacturing process itself.
As researchers like Mikhalchek have shown, any one of these tiny, almost invisible imperfections can become the starting point for a total, catastrophic failure.
So when you put all this incredible work together, the nonlinear mechanics, the vibration analysis, the stress modeling, where does it all lead? I mean, what's the actual payoff?
Well, this isn't just some abstract theory. This deep, deep science is leading to tangible breakthroughs that are making our physical world better, safer, and a whole lot more efficient.
The payoff is huge. We're talking more reliable and stable cars, safer aircraft. It enables wild new technologies, like systems that can harvest energy just from vibrations. It gives us lighter composites, those innovative metastructures that can be programmed to behave in specific ways. And, at the end of the day, just longer-lasting, more durable components in everything we build. So, the next time you see a simple spring, just remember that it's not simple at all. It's a gateway. It's a physical manifestation of some of the most advanced and difficult challenges in all of modern engineering.
And that really leaves us with a final thought, doesn't it? As we keep pushing our technology to be smaller, faster, and more resilient, the silent, hidden science of components like the spring, well, it won't just be important, it's going to be absolutely fundamental to shaping the world of tomorrow.